So this is the progression of my research so far. The system is currently set up, sorry, we have this power supply right here. It has anti-short circuiting measures in it to prevent amperage from getting over, I believe it's 5 amps to any specific circuit. This circuit pulls approximately 1.2 amps, where this old-fashioned oscilloscope pulls about 3 amps, except for it's isolated because, you know, it's an oscilloscope. So basically what happens is the power runs through the primary, oscillates to the secondary, generates the field, which then feeds through to the secondary input, which feeds back into the circuit and cuts it off. That's all explained in my presentation. Here we have the receiver. This looks large, but it doesn't have to be that large. I simply have it that way for demonstration purposes. These coils can be pressed down into a thin ring similar to the one which is present inside of your phone. So that's just background stuff. Here we have, I switched this out from the full bridge rectifier to the single diode rectifier. What that does is it changes the waveform from just positive, from dual positives to just monopositive, which means that the smoothing capacitor is going to have to do a lot more lifting, but that's not as important for the situation. So I'll go ahead and power this system on. It takes a second for the oscilloscope to warm up. But here you can see the LED. That's the regulating diode to prevent the negative voltage on the circuit from getting below 0.7 volts to prevent burnout of components and stuff. I made it an LED because it looks cool. And then here we have the oscilloscope. Now, when disconnected from the load, you can see that it generates a sinusoidal waveform of about peak to peak 10 volts, as each one of those is 5. I can actually switch it over to the 2 volt, and then here's 1 volt. So yeah, peak to peak about 10 volts. Which is useful as that gives us a metric by which to measure it, which means that its actual transference into the air is about, it's a pretty good efficiency, about 10 over 12, whatever that percentage is. And that efficiency is mainly because in the circuit right here, the regulating resistor is 470 kiloohms, which would drop it by an expected amount. So its efficiency is relatively high considering the inductance. So it generates that field, and then it feeds through this capacitor, and then it feeds through that inductor right there, which then feeds around into the circuit right here. And I can actually remove the smoothing capacitor to demonstrate what the circuit looks like without a smoothing capacitor on it. Here we go. Switch that to a DC measurement and connect it. You can actually see that it jumps way out of the circuit range. We actually have to adjust position to see it. And here I can actually invert the circuit diagram. There's going to be one small problem, and that's one small generic inefficiency or measurement inefficiency. You can sort of see them right there. They just sort of hop on a line. It's too high voltage to be easily measured though by this guy because it only measures about 15 volts. The main problem here is you can see here, this sort of loops up, which is going to create inductance with the capacitance field. That's not too big of an issue, and it can easily be fixed when it's soldered down to a circuit. But now for measurement purposes, it will be like that. We can actually check it by grounding that right there. So that's the circuit right there without the smoothing capacitor. But that's just power pull. You can actively actually see power transmission here. It can get about 6 inches, or that would be about 16 centimeters of power transmission of 13 watts to excite a fluorescent bulb. Now, that's not all the power it can pull, that's just the amount of power it can pull to excite that bulb. So if we introduce the smoothing capacitor right here, with negative polarization to the output of the single diode, we can insert it right there. And what that will do is that will give us a DC voltage when we adjust it to ground of about, that looks like about 3 volts. The reason why it looks so shaky like that is because as it is just one smoothing capacitor, it's actually going to operate as a square waveform based upon the load which is placed upon that single capacitor. Now, this can be fixed in the future by adding more smoothing capacitors. Additionally, the power output can be increased in wattage, or not wattage, but can be increased in voltage by increasing the amount of turns, which decreases the amperage, but that can be checked by a Marx generator. You can see that as we move its distance, its power remains relatively constant, only shifting a couple decivolts. And that's by design. The circuit has a capped pole almost by this diode right here, which prevents it from overheating and also prevents it from overpulling. This can have a range of that pole of several, almost a foot, I believe. Second, the power supply disconnected. Of almost a full 2 feet, I believe. Yep. There you go. A full functionality of about 2, or that's about a foot, but you can get all the way back to about, yeah, power transfer operates up to about 2 feet with about 2 volts. So there you go. There's the progress I made so far in my research in terms of material output.